Trigonometric integrals. Suppose we wish to evaluate the integral of cosine to the third power of x dx. We can try u substitution here, but what exactly would we let u be equal to? We could try letting u equal cosine of x, but then du would be negative sine of x dx. And this is a problem since we don't have a sine function in our integral. So for this, we need to try a slightly different strategy. Instead, what we're going to do here is rewrite the original problem by expressing cosine to the third power as cosine squared of x times cosine of x dx. Now the idea here is that I want cosine of x dx to end up being du. But for that to happen, u would have to be sine of x. But what I can do here is I can change cosine squared of x using the Pythagorean identity to be 1 minus sine squared of x. So if we just apply this identity, we're going to have 1 minus sine squared of x times cosine of x dx. And now, if we let u be equal to sine of x, du will be cosine of x dx, and this integral becomes 1 minus u squared times du. And now we have a very simple integral to do. We know the antiderivative of 1 is simply going to be u, minus the antiderivative of u squared is u to the third power divided by 3, plus our constant of integration. But remember, you have to go back and resubstitute the original function back in. So if u is equal to sine of x, we have sine of x minus sine cubed of x divided by 3 plus c. And you can write your answer like this, or you can also write your answer in this way. It's really just personal preference. What's important here is that you recognize both of these as being the same. Now let's talk a little bit about the strategy that I used to do this problem. So what made this problem work was the fact that we had an odd power of cosine. And that means that when we pull out one factor of cosine, we will have an even power left over. And it's very important that this power here is even, because that allows us to use the Pythagorean identity, cosine squared of x equals 1 minus sine squared of x. So the original power of cosine needed to be odd for us to be able to do what we did. Let's try a slightly more complicated example. Here we have the integral of sine to the fifth power of x times cosine squared of x dx. Now notice that the power of cosine is not odd. So the strategy that we used in the last problem is not going to work here. However, the power of sine is odd. So what if we tried the same strategy that we used for the last problem? Let's try it out and see what happens. So I'm going to rewrite sine to the fifth power as sine to the fourth power of x times sine of x. And then we have times cosine squared of x times dx. Now this time what I did is I pulled out one of the factors of sine here. So let's take that factor and let's write it next to dx. If we do this, we have sine to the fourth power of x times cosine squared of x times sine of x dx. And the whole point of doing this is that we want sine of x dx to be du. But for that to happen, we would have to let u be equal to cosine of x, right? Because if u is cosine, then du would be negative sine of x dx. And again, we're not worried about the negative. We can adjust for that. But the whole principle here is that I'm going to let u equal cosine, and then du will contain the sine that we need. So the only question is, what do we do with sine to the fourth power? Well, again, we need to rely on the Pythagorean identity. We know that sine squared of x is equal to 1 minus cosine squared of x. So now let's just remember that sine to the fourth power of x is the same as sine squared of x squared. But if sine squared is 1 minus cosine squared, we can put that in here, and that's going to give us 1 minus cosine squared quantity squared. So all this to say that we can express sine to the fourth power in terms of cosine. So if I do that here, we're going to get the integral of sine to the fourth power, which is 1 minus cosine squared of x, quantity squared, times cosine squared, times sine of x dx. And now we already have the substitution. And so if we just let u equal cosine, du is negative sine. So let's go ahead and adjust for the negative here. I'll put a negative in front of sine of x, and I will put a negative 1 on the outside of the integral. And now we can substitute directly. This becomes negative integral 1 minus u squared squared times u squared, and then negative sine of x dx is du. And now we just have the integral of a polynomial. So the next steps are a little bit tedious. We just need to multiply this out. So 1 minus u squared, quantity squared. Remember, this is 1 minus u squared times 1 minus u squared. And if you multiply this out, you should get 1 minus 2u squared plus u to the fourth. And then don't forget, it still needs to be multiplied by u squared. So next we will distribute u squared to each of these. And that's going to give us u squared minus 2u to the fourth plus u to the sixth du. And then finally, we take the antiderivative. So we have a negative. We need parentheses because this negative applies to the whole integral. And so the integral of u squared is u cubed divided by 3, minus 2 times the integral of u to the fourth is u to the fifth divided by 5, plus integral of u to the sixth is u to the seventh divided by 7, plus c. Now keep in mind that we're not done. We need to do two things here. We should distribute the negative, and then we should also plug u equals cosine back in here. So that first term is going to be negative cosine cubed of x over 3. And then the minus makes a plus 2 cosine to the fifth power of x divided by 5. And then minus cosine to the seventh power of x divided by 7 plus c. And we can leave our answer like this. Or once again, you could change the coefficients to be fractions. So we could say this is negative 1/3 cosine cubed plus 2/5 cosine to the fifth and minus 1/7 cosine to the seventh. Both answers are fine, and you should just make sure that you could recognize both of these as being the same. So in our next example, we need to deal with the prospect of not having an odd power of sine or cosine. So in this problem, we have the integral of sine squared of x. Now, to do these, it's a completely different process. What we need to remember is that there is a trigonometric identity that tells us that sine squared of x is 1 minus the cosine of 2x divided by 2. Likewise, there is an identity for cosine squared of x, which is very similar. It's 1 plus the cosine of 2x divided by 2. So for even powers of sine and cosine, you'll be using one or both of these identities. So let's go ahead and get into this particular problem. We have the integral from 0 to pi, sine squared of x dx. So what I'm going to do is just directly substitute 1 minus cosine of 2x divided by 2 in for sine squared of x. So if we do that, we get the integral from 0 to pi of 1 minus cosine of 2x divided by 2 dx. Now it's worth mentioning that the 2 here you can factor out of the integral. Now when you pull it out to the integral, it is in the denominator, so it comes out as a 1/2. And then we have 1 minus cosine of 2x dx. All right, so next we're just going to integrate each one of these terms. So what is the integral of 1 with respect to x? Well, it is x minus, and then here's the important one. What is the antiderivative of cosine of 2x? So remember, we have a formula for this. It comes from u substitution, but we should know at this point that the antiderivative of cosine of 2x is 1/2 sine of 2x. And then we're going to evaluate this from 0 to pi. So plugging in pi, we get 1/2 pi minus 1/2 sine of 2 pi minus, and then when you plug in 0, you get 0 minus 1/2 sine of 2 times 0. Let's keep in mind that this 1/2 power in front here applies to this whole thing. And then, of course, sine of 0 is 0. This is 0. Sine of 2 pi is also 0. So in the final analysis here, we just get 1/2 times pi, which can be written as pi over 2. In our next problem, we have the integral of sine to the 4th power of x. So once again, notice that we do not have an odd power of sine, nor do we have an odd power of cosine. So we're going to have to use these half-angle identities once again. And actually, we're only going to have to use the first one. So let's go ahead and apply it. We have the integral of sine to the 4th power. So how do we use it? Well, we need to remember that sine to the 4th power can be written as sine squared quantity squared. And sine squared is 1 minus cosine of 2x over 2. And then we're going to square that. And so this becomes the integral of 1 minus the cosine of 2x all over 2 quantity squared dx. All right, so now how do we do that integral? Well, let's first just do the squaring process. So we are going to square the numerator, and we're going to square the denominator. The denominator is a 4 there, so we can pull out a 1/4, and then we're going to multiply this out, 1 minus cosine of 2x times 1 minus cosine of 2x. And when you do that multiplication, you get 1 minus 2 cosine of 2x plus cosine squared of 2x. Okay, so now it's time to do the integration. So we know the integral of 1 is just going to be x. We know the integral of cosine of 2x is 1/2 sine of 2x. We just talked about that one. But then look here, we have the integral of cosine squared. Well, we can't do the integral of cosine squared, at least not directly. So we actually need to use this second identity down here. But there's another thing. We don't have cosine squared of x. We have cosine squared of 2x. So let's remember that when you have a half-angle identity here, the idea is very simple. Whatever this number is here, whatever this angle is here, this is just going to be 2 times that angle. So a more general form of the identity here is you can think of this as being theta. And then over here on this side, it's just going to be 2 times theta. So in other words, if you have a 2x here, on the other side, you're just going to have a 4x there. So cosine squared of 2x is 1 plus cosine of 4x divided by 2. So let's go ahead and put all that in here. We have 1/4 integral 1 minus 2 cosine 2x plus 1 plus the cosine of 4x divided by 2. Now you'll notice that even though I could do the integration on these two, I am waiting to do all of the integration at the same time. Now, you got to be really careful here. You have a 2 in the denominator. You cannot factor that 2 out to the front here because you do not have a 2 in the denominator of these here. So instead, I'm just going to break this up into two integrals. So I have 1 minus 2 cosine of 2x plus, and then I have 1 divided by 2 plus cosine of 4x divided by 2. So I'm breaking that up as a fraction with the same denominator, which in essence is creating another integral. But one last thing I can do before I actually integrate is notice that we have a 1 here plus a 1/2 there. We can add those together. 1 plus 1/2 is 3/2 minus 2 cosine of 2x plus, and then I'm going to make one small adjustment here. The 2 there, I'm going to write that as 1/2 cosine of 4x dx. So now we are ready to take the antiderivative. So we have 1/4 multiplied by the antiderivative of 3/2 is simply 3/2 times x minus 2 times the antiderivative of cosine of 2x is 1/2 sine of 2x plus 1/2 times the antiderivative of cosine of 4x is 1/4 sine of 4x plus c. And so the last thing we need to do is just distribute 1/4 to all of these, simplify what we can so we can cancel the 2's here, for example. And when we do that, we're going to get 3/8 x minus 1/4 sine of 2x plus, right here we have 1/8, but then multiplied by 1/4 is going to be 1 over 32 sine of 4x plus c. And this is our final answer here. So now let's just summarize our strategy for evaluating integrals of sines and cosines. If the power of cosine is odd, so what they do here is they say n is equal to 2k plus 1. Okay, that's just another way of saying odd. Okay, 2k plus 1 just means odd. Why does 2k plus 1 mean odd? Well, if k is an integer, right, let's say k equals 3, then when you multiply 3 by 2, you get 6, so that's always going to be even, but then when you add 1, you get an odd. Okay, so when they say 2k plus 1, they're just saying an odd number. So if n is an odd number, you save one factor of cosine, and you let cosine squared equal 1 minus sine squared to change the remaining factors in terms of sine. So when you look at this, I really do feel like this is kind of confusing. But just go back to the first and second examples that we did. Okay, and then in part B here it says if the power of sine is odd, then you save one factor of sine and you change the remaining factors of sines into cosines. And then it says if both the powers of sine and cosine are even, then you use the half angle identities. And these are the half angle identities that I talked about just a few moments ago. And I did write those identities a little bit differently. So I do want to point out that, I wrote sine squared is 1 minus cosine of 2x divided by 2. What they do is they factor the divided by 2 out as a 1/2. This is an alternative way of representing that same formula. And then they did the same thing for cosine squared. Okay? All right. And then it says here, it's sometimes helpful to use the identity sine times cosine is 1/2 sine of 2x. This is the double angle identity for sine. But I wouldn't memorize these processes. I would memorize the idea behind them, which was when you have an odd power, you save a factor so that it can become your du. And then you have to make it work with your u substitution. Now let's talk about integrals of secants and tangents. So here we have the integral of tangent to the 6th power of x times secant to the 4th power of x. And what's really important to remember here is that the derivative of tangent of x is equal to secant squared of x. So I'm going to take that approach here. I have the integral of tangent to the 6th power times secant to the 4th power dx. Since I have an even power of secant, I can pull out a secant squared. So let's go ahead and do that. I'm going to pull out a secant squared to be next to my dx. And if I do that, I will have a secant squared left over, because secant to the 4th is the same as secant squared times secant squared. And then, of course, we have tangent to the 6th power as well. Now, why am I doing this? Well, again, I'm identifying that secant squared of x times dx, I want that to be my du. But the only way that works is if u is equal to tangent of x. And again, because the derivative of tangent is secant squared. Okay? So if I do all that, I've got my du right here. Right here, I've got u to the 6th power. But then the big question is, what do we do with secant squared? Well, we use an identity. So we need to remember that secant squared of x is equal to 1 plus tangent squared of x. This is the Pythagorean identity for secant and tangent. So let's go ahead and make that substitution here. So I have tangent to the 6th power. We're going to leave that alone. This secant squared right here is going to become 1 plus tangent squared. And then times secant squared dx. Now this substitution that I have right here works perfectly. So if u is tangent, we have u to the 6th. If u is tangent here, we have 1 plus u squared. And then du is secant squared of x dx. And now we are simply integrating a polynomial. So we'll multiply this out first. And then we'll take the antiderivative. Make sure we add our constant of integration. But then the final step, you need to make sure you put your original function back in. So this is going to become 1/7 tangent to the 7th power plus 1/9 tangent to the 9th power plus c. So again, what made this work was the fact that we had an even power of secant. Now, why do we need an even power of secant? Again, because we wanted to pull out one secant squared. And the idea is when you pull out your secant squared, you need an even power left over to use the Pythagorean identity. So since you're taking out two factors of secant here, you need an even number so that you have an even number left over after you take two factors out. So it's the same idea as what we did with sine and cosine, but we're just looking for something different because the derivative of tangent is secant squared. In the next example, notice that we do not have an even power of secant. So if we try to use the same strategy, it's not going to work. And that is because, let me just show you here, if you pull out a secant squared from secant to the 7th, you'll have secant to the 5th power left over. The problem is you cannot use a Pythagorean identity to transform secant to the 5th because a Pythagorean identity only applies to even powers, right? So remember, we know that secant squared of theta is 1 plus tangent squared of theta. So if I have secant to the 4th power of theta, I can think of that as 1 plus tangent squared, quantity squared. Or if I have secant to the 6th power of theta, I can think of that as 1 plus tangent squared, quantity cubed, right? So if I have an even power, I can convert the power of secant into a power of tangent. But if I have an odd power, I cannot do this, okay? And that is why this odd power of secant in the beginning doesn't help us. Because after we take out the secant squared, we still have an odd number there, and that's no good. So we need a different strategy. So here the strategy is, actually we have an odd power of tangent. That's the one that's going to make this work. Now when you have an odd power of tangent, here is what we're going to do. We're going to pull out a factor of tangent, and we're also going to pull out a factor of secant. So if I pull out one factor from 5, we're going to have tangent to the 4th. And if I pull out one factor of secant from 7, we will have secant to the 6th. And these are thetas, not x's. Okay? Now, I did pull out a factor of secant, and I pulled out a factor of tangent. Okay? So all I'm doing is taking out one factor of each of these and putting it off to the side here. And when I do that, it reduces the power of each one of these by 1. Now, why am I doing this? Well, it's because I want this to be du. But you know, the only way du can be secant theta tangent theta d theta, the only way that can happen is if u is equal to secant, right? Because the derivative of secant is secant tangent. So, if this is going to be our du, u has to be secant, so this is perfect. We have basically u to the 6th power here, but then the big question is, what do we do with these? Well, again, we know what to do. We use a Pythagorean identity. So we just said a minute ago, secant squared of theta is equal to 1 plus tangent squared of theta. Well, that means that tangent squared of theta is equal to secant squared of theta minus 1. And then we know that tangent to the 4th power of theta is tangent squared, quantity squared. But tangent squared is secant squared minus 1, and so tangent to the 4th power of theta is secant squared of theta minus 1, quantity squared. So once again, we are going to use a Pythagorean identity to rewrite tangent to the 4th in this way. And then don't forget, we still have secant to the 6th power, and then we still have secant theta, tangent theta, d theta. So now we're going to apply our substitution. So when we put this in here, this becomes the integral of u squared minus 1 squared times u to the 6th times du. And then we just have to be patient and multiply everything out. So u squared minus 1, when you FOIL that to itself, you get u to the 4th minus 2u squared plus 1 times u to the 6th times du. And now we're going to distribute u to the 6th. That is going to give us u to the 10th minus 2u to the 8th plus u to the 6th du. And now when we take the antiderivative, we get 1/11 u to the 11th minus 2 over 9 u to the 9 plus 1/7 u to the 7th. And then I've been saying plus c, but I got to tell you a little tip here. I don't like putting plus c until after I put our function back in the problem. So I'm going to write this as 1/11 secant to the 11th of theta minus 2/9 secant to the 9th of theta plus 1/7 secant to the 7th of theta. And now that I've plugged it back in, I'll say plus c for my final answer. So in summary, when integrating powers of secant and tangent, if the power of secant is even, we're going to save a factor of secant squared and then use secant squared equals 1 plus tangent squared, and then we're going to let u equal tangent of x. So just look at the example that we just did for guidance on that. If the power of tangent is odd, we're going to save a factor of secant and a factor of tangent, and we're going to let u equal secant of x. Okay, so these are the general guidelines. If neither one of these is true, then you have to just try to see what you can do to make it work. And we're going to see a couple of examples of that here in just a minute. But these are just guidelines, and it's important for you to understand the context of how they work. I don't want anybody trying to memorize these guidelines. What you need to do is memorize that you can use substitutions and that you just have to make the right substitution for these problems to work. Now here's an integral that is good for you to memorize, and it is the integral of tangent of x is equal to the natural log of the absolute value of secant. This is a classic formula that most calculus students should memorize. Now, I'm going to show you why this formula is true. So when you integrate tangent of x, what you're going to do here is change tangent into sine of x over cosine of x by simply using the ratio identity for tangent. Now from here, I'm going to apply a u substitution. I'm going to let u equal cosine, and then du is going to be negative sine. And so to make this work, I need to put a negative in front of the sign here, and I need to put a negative 1 on the outside. And this becomes negative integral of du over u. And we know that this is negative natural log of the absolute value of u, and that becomes negative natural log of the absolute value of cosine of x plus c. Now you'll notice that in the formula here, that's not what they have. They have something a little bit different. So let's just go through this. If you think of this as a negative 1, remember that there is a property of logarithms that allows you to bring this up as a power. And so this becomes natural log of the absolute value of cosine to the negative 1 power. But the absolute value of cosine to the negative 1 is 1 over the absolute value of cosine. And that is the same as the natural log of the absolute value of secant, because the reciprocal of cosine is secant. So that is why you get what you get here for the final result. But this is a good one to memorize. Another classic integral that you should memorize as a calculus student is the integral of secant is the natural log of the absolute value of secant plus tangent. And this one's a little bit tricky. So let's talk about how you get this result. What I'm going to do is take the original integral, which involves the function secant of x, and I'm going to write it as secant over 1, and then I'm going to multiply the top and bottom of that fraction by secant of x plus tangent of x. Now, there's no reason to want to do this, except that once you've seen that this works, then you know that this is kind of the trick that you need to do here. So now in the numerator here, I'm going to multiply secant times secant and secant times tangent. And just for convenience, I'm going to reverse those. So secant times secant is secant squared plus, and then secant times tangent is secant x tangent x. And then in the bottom, we just have secant x plus tangent x dx. So it looks pretty messy. But now what I'm going to do is let u be equal to secant of x plus tangent of x. And the reason for this is because du will be secant tangent plus the derivative of tangent, which is secant squared, and then all that times dx. So you'll notice that you have exactly du on top and exactly u in the bottom. And so this becomes the integral of du over u, which is the natural log of the absolute value of u, which in this case is the natural log of the absolute value of secant of x plus tangent of x plus c. Okay, now back to some more examples. How do we find the integral of tangent cubed? So notice that we have an odd power of tangent, but we do not have a secant to go with it. So sometimes you just have to try stuff and see if it works. And I know that sounds maybe dismissive, but it is true. Sometimes with integration, you just can't be afraid to try things by using rules of exponents, identities for trigonometric functions, or u substitutions, etc. So when we have the integral of tangent cubed, I want you to notice that I can rewrite this as the integral of tangent squared times tangent. And then from there, we're going to remember that tangent squared of x is the same as secant squared of x minus 1. And I'm going to plug this in for tangent squared. So this becomes the integral of secant squared of x minus 1 times tangent of x times dx. Okay, so maybe now it doesn't seem like we've gotten anywhere, because if you try a u substitution at this point, it's not really going to work out well for you. But let's go ahead and distribute this now. So I have tangent times secant squared minus, and then tangent times 1 is just tangent. And now from rules of integration, I can break this apart into two integrals. So I have the integral of tangent x secant squared of x dx minus the integral of tangent of x dx. And now it's starting to come together. For the first integral, I can let u equal tangent, and du will be secant squared of x. And that integral becomes the integral of u du, which we know is u squared divided by 2. But of course, u is tangent, and so this first integral becomes 1/2 tangent squared of x. Minus, what about the second integral? Well, that's the integral of tangent. And just a minute ago, we said that this is one that you will want to try to memorize because it comes up a lot. So the integral of tangent is the natural log of the absolute value of secant. And then we have a negative in front because there is a negative here, which came from the identity. And that's it. This is our antiderivative. Now our next example is a classic example of integration, the integral of secant cubed. Now the technique to use here is actually integration by parts. So let's go through it. We have the integral of secant cubed x dx. We are going to choose u to be secant of x and dv to be secant squared of x dx. Now, why is this my choice? Well, one, we know that when we multiply these, we have to get secant cubed. But why did I choose these the way that I did? Well, simple. If dv is secant squared, then v is the antiderivative of secant squared, which we know is tangent. And if u is secant, then du is secant tangent. And then by integration by parts, we're going to multiply u times v together, which is secant x tangent x, and then minus the integral of v times du. And that is tangent of x times secant of x tangent of x dx. So we have secant of x tangent of x minus the integral of secant of x, and then tangent times tangent is tangent squared of x dx. Okay, so now the question becomes, what do we do with this? Well, we could try letting tangent squared be equal to secant squared minus 1. So I'm just going to use a trig identity there. So we have secant of x times secant squared of x minus 1 dx. I'm going to multiply this out. This gives us secant of x tangent of x minus the integral of secant cubed x minus secant of x dx. Now, let's separate this into two integrals. We have secant x tangent x minus the integral of secant cubed x dx, and then minus minus becomes a plus the integral of secant of x dx. And let's remember that this is the integral of secant cubed that we're looking for. So what you should notice is that you get the original integral you were looking for here, right? That's what we're trying to find. And when that happens, what you can do is add that quantity to both sides. So I'm going to add the integral of secant cubed to both sides. When we do this, we get 2 times the integral of secant cubed. And on the other side, we have secant of x tangent of x plus the integral of secant of x. But the integral of secant of x, that's that integral that we just did a moment ago that I said you should memorize. And what is it? Well, it is the natural log of absolute value of secant of x plus tangent of x. And this is all equal to 2 times the integral of secant cubed. So what is secant cubed? Well, we're just going to multiply both sides by 1/2. That will cancel this out. And we end up with the integral of secant cubed x dx is 1/2 secant x tangent x plus 1/2 natural log of the absolute value of secant of x plus tangent of x plus c. So the main thing I want you to take away from this section is that you just have to be willing to keep trying things, whether it's U substitutions, integration by parts, trig identities, algebraic simplification, etc. The main thing is you can't quit. You just got to keep trying until you get things to work. And that concludes this video lesson.